about creating a transition diagram or matrix from a word problem. So remember these 2 bullet points. These are things that I've already said, but they're phrased in a little more technical language. So here, remember that Tij is the probability of moving from the state represented by I to the state represented by j in a single transition. So it's the probability of moving from the ith state to the jth state, assuming you were in the ith state. And also each state, whenever you make a diagram, is going to be represented by a circle, and we're going to draw arrows between the states to represent those transition probabilities between each of those states. So let's look at example 4. Here, a math department has 2 classrooms, A and B. After each class period ends, a student in room A has a probability of 0.7 to leave the room and go to room B, while a student in room B has a probability of 0.4 to leave room B and go to room A. And now we want to draw the transition diagram and the transition matrix for this situation. So in the previous examples, we practiced a little bit taking a diagram and turning it into a matrix. So this time, I think just to switch it up, let's first make the matrix, and then after that, we will make the corresponding diagram. So if I wanted to make the matrix, remember the transition matrix needs to describe the probabilities of transitioning out of this current state, either A or B, into the state A or B. So let's pretend that our current state is A. In other words, we're currently in room A, and we want to know where we're going to land next. So this is a probabilistic statement. We don't know whether we're going to move to A or B, but we do know what the probability is of each of those transitions happening. So we know that a student in room A has a probability of 0.7 to leave room A. So that means that we must be going from A to B. So this probability would be 0.7, or 70% if you want to phrase it as a percentage. Next, we have the transition probability from A to A. Now notice that's not explicitly stated in the prompt, but we do know that if there's a 70% chance that you leave the room A, then there's a 30% chance that you stay. And that can also be found by remembering that each of these rows has to total up to 1. Those are just 2 different ways of saying the same thing. Both of those are just saying that the total probability here of those transitions away from A, that total probability has to be 1. Just like if there's a 20% chance that it rains tomorrow, then there's an 80% chance that it doesn't rain tomorrow. Total probabilities need to be 1. Okay, so next, we'll look at the transitions away from B. So it says if a student is in room B, then they have a probability of 0.4 to leave room B. So that means that they would be going from B to A with a probability of 0.4. So that means that this entry should be a 0.4, and therefore this last entry has to be a 0.6, because that bottom row has to sum up to 1. In other words, they have a 60% chance, if they're currently in room B, of staying there during the next time step. So this T you can think of as representing transition, but sometimes I like to think of it as representing T for time, because this is saying what the next step is going to be. So if you're currently in A, it's telling you what the next step will be, either A or B, but it's doing so in a probabilistic way, because we don't know exactly whether a given student is going to be moving from A to B, but we do know their likelihood of moving from A to B. So this is our transition matrix. If we want the corresponding transition diagram, we first can just make a node for each of the states. So we have the state A and the state B. And then we can use the diagram to fill in all of the arrows and their weights. So if I want the transitions away from A, I have the possibility of going from A to A, and I also have the probability or the possibility of going from A to B. And for the weights on these arrows, remember those are supposed to represent the transition probabilities there. So if I want to put a weight on this arrow from A to A, then that arrow would have the weight 0.3, because that's the probability of transitioning from A back to itself. And similarly, this top arrow here would have the probability 0.7 attached to it, because that's the probability of transitioning from state A to state B. And then similarly, maybe just to make sure that you're following, why don't you decide what you think this arrow should have as its label? So the arrow that goes from B to A, you can pause the video if you need to think about it, but this is going to correspond to the transition from B to A, which lives here in the transition matrix. So that would be a 0.4. And again, either by reading it from the matrix or because we know that these outbound arrows from B have to total up to 1, I can see that this last arrow has to have a weight of 0.6. So this would be my transition diagram. Usually if you're making a transition diagram, you want to start by just writing down all of the different states that you have, so state A and state B, and then you can draw outbound arrows for all of the different transition probabilities. And then similarly for the state T, or sorry, the transition matrix over here, we're just recording all of the information that was given to us in the prompt in a different way, or in an equivalent way, I should say. So these are just two different ways of presenting exactly the same information. And now we can do the same thing in example 5. I'm going to go a little bit more quickly here because I sort of suspect that you're following, but if things still seem confusing, I would recommend just pausing this video and going back over the first few minutes of the first video, because now you've seen sort of where these examples go. But let's look at example 5. So Alice, Bob, and Kathy are taking turns playing a game. I'm gonna just label them A, B, and C for convenience. Each person is taking a turn, and then they either decide to keep the game for a second turn or hand it over to one of the others. And we have these transition probabilities given to us in the prompt. So if you want, you can pause the video and read through the prompt. I'm just going to collect the information as we need it. And here it says, let's draw a transition diagram and write the transition matrix for this situation. So I'm going to start with the diagram since we did the matrix first in the last example. But it doesn't matter which one you start with. I think if the matrix confuses you, then it might be best to just start with the diagram and then translate that diagram. But either way, you can just build one and then translate to the other form. So here, if I want to start putting arrows in, now that we've got our 3 states, I need to decide the probabilities of transitioning away from each of these. So let's start with the probabilities of transitioning away from A to the others. So let's say that Alice has the game currently. Now we're going to try building these probabilities, the probability of transitioning from A to B, A to C, and also A to itself. So those are the 3 things we're looking for right now. And for this, we can just look at this sentence that I started to underline. Alice is going to keep the game with probability 1/2. So that's a transition from A to A in the next time step. She's going to hand it to Bob with a probability of 1/3 after her turn, and she's going to hand it to Kathy with probability 1/6. Now, here, the weights on each of these arrows, they can be written as decimals or percentages or fractions or whatever, but they need to represent a probability. So it'll be some number between 0 and 1, or written as a percentage between 0% and 100%. But these are the outbound arrows from A. And we can similarly find the outbound arrows from B and C. So if we want the outbound arrows from B, it says Bob hands the game to Alice with probability 1/4. So that would be going from Bob to Alice with probability 1/4. If Bob currently has the game, he keeps the game with probability 1/4. And by the way, even if this information was not here, so even if we didn't know the probability that he hands it to Kathy, we already have enough information here. So, in other words, if I just had the diagram, I didn't have the words up above, if I just had the diagram in its current state, I could still fill in that this arrow has to have a 1/2 weight, because I know that this outbound arrow from B has 1/4 weight, this one has 1/4 weight, and the total of outbound arrows, the total of their weights, has to add up to 1, because those are the probabilities of transitioning from B to each of the respective states. So if there's a 1/4 chance we go from B to A and a 1/4 chance we go from B to B, then the remaining 50% chance must be a transition from B to C. So therefore, this one would have to be 1/2 even if we didn't have that information directly given to us in the prompt. And then lastly, for these arrows from Kathy, Kathy is handing the game to Alice with probability 1/5, so that would be, whoops, that would be an arrow from Kathy to Alice with probability, sorry, that's 1/5. And then Kathy is going to hand the game to Bob with probability 3/5, rather. So this one will be 3/5. Sorry, these labels are a little bit ambiguous, but hopefully you'll just be a little more careful than I was when drawing your diagrams. I'm not going to be too persnickety about them, but just try to avoid situations like what I just did here, where it's a little unclear which one of these is describing which. And lastly, she's going to keep the game with probability 1/5. So that would be a Kathy to Kathy transition with probability 1/5. So this is our transition diagram. And now we can make the corresponding transition matrix. So I usually like to call it T. I'm just going to use the natural alphabetical ordering for these states. And we can then just read either from the prompt or from the transition diagram that we've written. So I think this might be a good time to pause the video and fill in this matrix yourself first, just to make sure that you understand what's going on. And then I'll quickly fill it in. So for this, I'm just going to read from the diagram to the left here. So I know that the probability of transitioning from a state A to each of these states is given by the outbound arrows from A. So I'm looking at arrows that go away from A. And we have a 50% chance of going from A to A, and then a 1/3 chance of going from A to B, and a 1/6 chance of going from A to C. And if you'd like, you can check these do add up to 1. So that's good. Transitions away from B, I think the place that people are most likely to get messed up is here. You might expect this to be a transition from B to B. So you might be tempted to look here for that information. But just be careful to note the column that you're currently looking at. So this entry, the 2-1 entry, is going to describe the probability of transitioning from B to A. So that would actually be this arrow here. So we get 1/4 as the B to A transition probability. 1/4 is also the B to B transition probability, and 1/2 was the B to C transition probability. And then for our last one, I'm just going to quickly fill them in. C to A has a weight of 1/5, C to B has a weight of 3/5, and C to C has a weight of 1/5. So those are our two equivalent ways of writing down the transition matrix or the transition diagram that we need for this Markov chain. And now in our next video, I'll talk about how to set up the probability that you're in a certain state at a certain time. And for that,